In the previous class, I have started teaching moving charge and magnetism. Not sorry, magnetism and matter. I finished moving charge and magnetism, and I started teaching magnetism and matter. And in magnetism and matter also, I have finished half part of it. I said that the chapter has two parts, but both parts are not much related. So no problem today, who are coming after a long time or those who are coming for the first class also will understand today's class, hopefully. Because the first part and the second part of chapter are not much linked, right? Now, for the students of SSM Nagar, I am going to come on Friday to SSM Nagar. Friday, those who are in SSM Nagar can come and learn from me. I am going to revise chapter 1, 2, 3 like that I will start. This Friday I am going to be there. I will mention the timing in the group. All the SSM Nagar children can come and assemble on this Friday. I will tell you what time. I will try not to disturb your regular class. Okay? Coming back. So, in the chapter magnetism and matter, let me recall whatever I have taught you. Believe me, it's simple chapter where they talk about only two things. One thing is magnetic materials, diamagnetic material, paramagnetic material, ferromagnetic material. How diamagnetism is occurring, the concept behind that, reason behind that, how paramagnetism is taking place, electron theory behind that, and what is ferromagnetism, domain theory behind that. So, first, that is diamagnetism is the result of electromagnetic induction. For teaching you that, I taught you EMI a bit, I taught you Lenz's law, then I came back to diamagnetism, and I hope I could make you understand what diamagnetism actually means, because I am very sure nobody will teach you in this much detail about diamagnetism. Para they will teach, but dia is something which is little vague, but whatever best I could do, I did for you. I told you which materials show diamagnetism. Diamagnetism is universal property. Every material will show diamagnetism. And why? I told that also to you. In paramagnetism, the reason behind that, electron theory behind that, I taught that to you. Then I taught to you about ferromagnetism. I also gave you the mathematical concept behind that. That is, what about its relative permeability? What about its magnetic susceptibility? Everything I spoke in the previous class. So, a video is there. If you have missed the class, check that and learn that. Remaining half of the chapter is what we are going to start today. So, basically this chapter, second part I have finished, the last part. I have not finished the first half. Today we will learn about the first half, and first half talks about the bar magnet. So, I told you that magnetism as a whole in 12th standard is made into two chapters in CBSE. One chapter is moving charge and magnetism, another chapter is magnetism and matter. In moving charge and magnetism chapter, they teach to you about how a magnetic field is produced by current carrying conductor. Current magnetic field, that only is discussed in chapter number 4. But chapter number 5 they talk about natural magnetism, that is how the magnetism takes place. What is the cause of magnetism naturally? And now we are going to learn about the properties of bar magnets. Okay? So, first of all, give the heading as basic properties of magnet. Give the heading as basic properties of magnet. Some very basic thing which you must know, not new for you, and they are like, first is directive property. Are you aware about this? Directive property. Are you knowing that if I have a bar magnet and I tie my bar magnet to a string, and if I hang it through the wall, then my bar magnet will turn and finally point in north-south direction? I hope you are aware about this. A magnet always points in north-south direction if it is hanging freely from a string and a ceiling. I hope you are getting what I am trying to say. From the ceiling, if I tie a rope and I put a magnet inside it, it will always stop in north-south direction. That property is called as directive property. Second property, much known to you, is attractive property. What is that? Attractive property. Like poles repel each other, and like poles attract each other. If you have a north pole, you bring a south pole, it will attract it. South pole bring a north pole, it will attract it. South pole bring a south pole, it will repel it. So attractive property is also including repulsion. So by this property, magnets attract and repel other poles. Not only that, magnet also attracts magnetic substances. Like if you have magnet, bring iron nails, it will attract it, isn't it? So magnet attracts the magnetic materials and it repels the same poles, the similar poles. The third property is about the property of monopoles. I hope you are aware that monopoles don't exist, does not exist. It can never exist. It means if you have a bar magnet which has north pole and south pole, you cut it. You get another two magnets which are having once again north, south and north, south. Once again cut it, the same thing will repeat. Even if I go in atomic level, I am going to have north, south, north, south, north, south only. Vignesh, if you are hearing me, video must be on in the class. Yes. So when you cut the magnet, you will never be able to get a monopole. If I ask you, get me a north pole, you can never get. North pole will come along with south pole only. In some diagram in the question, if you are seeing like this, north pole, south pole, magnetic field is going from north pole to south pole. Imagine that there must be some south pole here, there must be some north pole here. Never imagine in the book they gave only north pole, sir, it means monopole exists. No, no. Monopoles never exist. Only dipoles exist. Dipole means both north and south pole. Very basic thing. I hope you understand what I said now. So monopoles never exist. These are some very basic properties of magnet. I hope everybody understands this. Need not to write much about it, just you can just write directive property, attractive property and monopoles don't exist. These are the basic properties of magnet. Make a note of it fast. Directive property means a magnet hanged from a string will always point in north-south direction. Attractive property means magnet always attracts the magnetic substances, also attracts the unlike poles and repels the like poles. Monopoles can never exist. It means that if a magnet is broken down into smaller fragments, we are going to get always dipoles, north, south, north, south, north, south. We never get monopoles. That is what is the fourth property of magnet. I hope you have written this, very basic thing. Next, I want to talk about some terms which are going to be used in today's class and you must be aware about those terms. So when I will talk about a magnet and suddenly I use the word, first of all, are you aware about north pole and south pole we say, right, in magnets? We say north pole and south pole. If I ask you, where is the exact position of north pole, what is your answer? Little bit inside. How much little bit? Little bit means how much? dx. 85% of the? Good, actually right. 85% of the geometrical length, this is called as geometrical length, and 85% or 0.85 times of geometrical length is called as magnetic length. So whenever I say the word magnetic length, it is the distance between the poles. What is magnetic length? It is distance between the poles. And where does the pole exist? Little inside. How much little? 85% of the geometric length is the magnetic length. So 0.75 here, 0.075 here, 0.075 here. If you go inside, there is a location of north pole and south pole. So never think that edge is north pole, edge is south. Many of you are thinking like this only. This is north pole, this is south pole. Or some of you are thinking half is north, half is south. Not like that. North is somewhere here, south is somewhere here. Little inside from the edge. That is the location of poles. And all the poles, they give rise to pole strength, which is represented by Qm. its unit is, I'll talk about this in today's class. Now you can just write, SI unit is what? Anybody knows? It is ampere meter. So, SI unit of pole strength is ampere meter. And what is pole strength? Pole strength is the strength of the magnetic pole. North pole, how much strong north pole you have, how much strong south pole you have. That strength is represented by pole strength of the magnet. We will use these terms today in today's class, pole strength. I hope you are understanding these things. Anybody knows what is this called as? The line joining the poles. Distance is called as magnetic length. Line joining the poles, it has a name. Anybody knows that? Line joining the poles is called as, that is, if I have a magnet and a line joining both the poles, is called as, pole length is distance. Line is called as what? It has a name. Magnetic? Tell louder. Yes, actually it is right. It's called as magnetic axis. Magnetic axis. And if I draw a perpendicular from here, that will be called as magnetic meridian. Sorry, magnetic equator. Magnetic equator. These terms you should know. Magnetic axis, magnetic equator. What are these things? You must be aware about these terms. Please. Nowhere you should forget these terms. Okay. So, I hope you are aware about these terms now. Suddenly, if I use the word magnetic length, you should understand what is the meaning of magnetic length. If I use the word pole strength, you should understand what is the meaning of pole strength. Okay. So, can I go to the next page? I am just giving introduction now. Now only I am going to start the chapter. After this only main topics will start. Shall I start? I hope I can. Karthikeya Balan, shall I start? Yes. So, give the heading as Coulomb's law in magnetism. Coulomb's law in magnets. Now, what I am going to do, you please pay attention. Now, whatever you are going to study is going to be analogous to first and second chapter. So, basically, we are going to recall first and second chapter, all the concepts. Today, whatever we are going to learn, you will feel that it has a similarity in first and second chapter. So, if you are having first and second chapter full clarity, today's class will be very simple for you. Otherwise, vice versa, it will be difficult for you. Okay. So, what does Coulomb's law says? Remember Coulomb's law? Force of attraction or repulsion between the two charges is directly proportional to product of their charges and inversely proportional to square of distance between them. Same way, for poles, there are two poles, right? If it is like poles, repelling, unlike poles, attracting. This force of attraction or repulsion is directly proportional to the product of pole strength and inversely proportional to square of distance between them. There we wrote F is proportional to Q1, Q2, F proportional to 1 by R square, and I combine that. Here I will write F proportional to QM1, QM2, F inversely proportional to R square, and I will combine both. I will write F proportional to QM1, QM2 by R square. If you want to remove proportionality, you have to add a constant, and that constant here is called as mu naught by 4 pi. F is equal to mu naught by 4 pi. into qm1 into qm2 by r square. Mu naught is same like the last chapter. What is mu naught? 4 pi into 10 to the power minus 7. It is permeability of free space. Don't forget that. This is Coulomb's law in magnetism. Very simple. Yes, Sharon.
Sir, you told about that R square.
Yes.
That R is the distance between poles.
Exactly. If you have one pole here, I am writing it as qm1. Another pole here, its pole strength is qm2. Distance between the pole is called as r. So if you take a magnet and check, it will be little inside the magnet. It's magnetic length for a bar magnet. But see, don't always imagine we are talking about the bar magnet. We can also take north pole from here, we can take south pole from here, and then I can find the force of attraction, no? So it's not like it should be of the same magnet. It can be of different magnets also, but then this will be the R value, not this will be not the R. I hope you're understanding my point. Yes, copy this fast. Those who have understood, please copy it. If you have any doubt, feel free to ask me. Devadarshan, if you are able to hear me. Camera should be on. If you have not forgotten after 2 weeks you are coming back, forgot the rules of the class itself. Written? Okay. So, please pay attention. After learning Coulomb's law in the first chapter, we learned about electric field. You remember? Electric field is defined as force per unit charge. So, what will be magnetic field? Force per unit. Electric field is force per unit charge. Charge is getting replaced by what? Pole strength. So, force per unit pole strength will give you magnetic field. Next heading is, write the heading as magnetic field produced by a magnetic pole. Magnetic field produced by magnetic pole. Magnetic field produced by magnetic pole. Magnetic field produced by magnetic pole. So, what will you write for that? Write a definition. Magnetic field is defined as force per unit pole strength. Force per unit pole strength.
Sir, can you repeat it, sir?
I will repeat, man. Magnetic field produced by a pole is given by force per unit pole strength. Force per unit pole strength. Basically, I am just replacing charge by pole strength here, Anshul, if you are understanding. So, there it is F by Q, here F by QM. Nothing much is happening. Okay. Then in your first chapter, you studied about something called as electric dipole. Give the heading as magnetic dipole here. Next heading is magnetic dipole and dipole moment. And dipole moment. So, if you remember, how did we define electric dipole? First chapter. Electric dipole is defined as arrangement of two equal and opposite charges separated by a small distance. What will be here? Write that. It is the arrangement of two equal and opposite poles separated by a small distance. The same thing. Write that. Arrangement of equal and opposite poles. Arrangement of equal and opposite poles. Equal and opposite poles separated by a small distance, separated by small distance. In bracket you can write 2D, same thing follows here also. In bracket you can write 2D. So QM, QM and distance is 2D. So to make you understand they are opposite, I am writing one thing as north, one thing as south. One more thing you can remember, please pay attention. If you know that if I have a plus charge and if I have a negative charge, the electric field goes from where to where? Positive to negative, isn't it? So positive it starts and it terminates in negative. Same way, here the charge goes from where? Magnetic field goes from north and goes in south. It means north will have similar behavior to positive charge and south will have similar behavior to negative charge. Just for a analogy I am saying. I am not saying north is positive, south is negative. The behavior of north pole will be similar to positive charge, behavior of south pole will be similar to negative charge. Now, you know very well about dipole moment also. What is dipole moment? Electric dipole moment is what? Charge times distance between them, Q into 2D. Here it will be pole strength times distance between them. Right definition of magnetic dipole moment, otherwise called as magnetic moment alone. Magnetic moment. It is given by M, obviously vector quantity M. And how it is defined? Magnitude of pole strength times the distance between the poles. Write it please. Magnitude of pole strength times the distance between the poles is known as magnetic moment. Magnitude of pole strength times the distance between the poles. The distance between the poles is known as magnetic moment. Magnetic moment. So M is equal to Q into 2D. QM actually, not Q. QM into 2D. Now please pay attention one second. I said that magnetic dipole is arrangement of equal and opposite poles and a small distance. Equal and opposite poles makes a bar magnet. If you have a bar magnet, it will have north south. So sometimes in books you will find instead of writing magnetic dipole, they will also write short magnet. So wherever you see the word short magnet, understand they are talking about what? Magnetic dipole. Because magnet has north and south and short means dipole. I hope you get my point. So wherever they use the word short magnet, it means they are talking about what? Magnetic dipole. But any magnet cannot be called as magnetic dipole. Any magnet cannot be treated as a magnetic dipole because it may have a bigger length, and for dipole you must have a short distance. So if I am having north pole, south pole, 2 meter distance between them, I cannot call it as a magnetic dipole. But if I am having north pole, south pole, 1 millimeter distance between them, it can be called as a magnetic dipole. So magnetic dipole are also called as short magnets. Okay. When you learnt about the electric dipole moment, it had a direction, you remember? Direction from where to where? Negative to positive. So here from where to where it will be? South to north. Write that. Direction of magnetic moment is from south to north. Direction of magnetic moment is from south to north. Direction of magnetic moment is from south to north. Okay. Now one more thing I will tell you. Pole strength, what is the unit I told you? Ampere meter, I told no? Yes, this is and into meter. So ampere meter into meter will become ampere meter square. So what will be the SI unit of magnetic moment? Write down somewhere. SI unit of magnetic moment is ampere meter square. Ampere meter square. So magnetic moment is given by ampere meter square. It is matching with what you studied in previous chapter. In previous chapter, suddenly out of nowhere, torque due to electric, that is torque on a current carrying coil kept in magnetic field. I told tau is equal to NIBA sin theta, and NIA I took as M. What is I? Ampere. Area meter square. Ampere meter square is also called as magnetic moment, I told. Say ampere meter square. And today we will also learn how I wrote magnetic moment as NIA. Today we will learn that also, if we reach that point. Okay, up to here it is clear? Any problem? It is just repetition of what we studied earlier, nothing much. Shall I proceed for further? I hope all of you are writing parallelly. Yes. Next topic is, so once again, in first chapter, after learning about electric dipole and dipole moment, you learnt about electric field due to electric dipole at an axial point. Same way here it will be. Next topic is magnetic field due to magnetic dipole at an axial point. There is 2 points will be there. First we will find for at an axial point. So I hope you remember how we derived. Same way we will derive here. So I am going to have 2 poles, QM and QM. One is obviously south, one is obviously north. And if you remember, wherever we want to find electric field, we used to bring a test charge there, you remember? If I want to find electric field, what we used to bring? A test charge. Here we will bring a test pole. So if I keep a test pole here, north for instance, this pole will repel it. Monopoles don't exist, but even then we are just keeping a test pole theoretically. The south will attract it. So I am going to have 2 kinds of magnetic field here, B1 repelling, B2 attracting. Which will be more, B1 or B2? Why B1 is more? Distance is small. Common sense. So if you see here, this is totally 2D, and from center of dipole, that is from here, I go r distance away, and this point is only called as axial point. So if this is D, D, R, this small distance will become r minus d, isn't it? And the whole distance will become r plus d. Do you agree with me? Up to this point. So when I find the value of B1, what I am going to get? B1 will become equal to mu naught, I mean, what is the formula? Because electric field was equal to kq by r square, you remember? So here magnetic field will become mu naught by 4 pi into qm by r square. Remember this. That is magnetic field produced by a pole will be mu naught by 4 pi into qm by r square. I should write it here itself. If you remember, when I told about magnetic field, I should have written that magnetic field due to a pole is given by mu naught by 4 pi into qm by r square. Very similar to electric field due to a charge, point charge, kq by r square. Here it will be mu naught by 4 pi into qm by r square. I told you everything is analogous. If you know chapter 1, you know chapter 5 automatically, half chapter at least. So same thing, I am going to continue here. So B1 will become equal to mu naught by 4 pi into qm by r square, not r square, it will become how much? How much it will become? B1 I am finding here. So it is from here to here. R minus d whole square. What about B2? mu naught by 4 pi into qm by r plus d the whole square. If you are thinking I am going very fast, actually I am not going fast. Since we have learned all these things, I am just going little quick because it is coming from the first chapter itself. The same thing I am doing. What I am doing, I have a dipole of distance 2d. From its center I am going r distance away, and here I am finding the magnetic field. So if I check from this pole, distance is r minus d. From this pole it is r plus d. So for this pole, what is the magnetic field? Repelling magnetic field, because north will repel. So B1 will become equal to mu naught by 4 pi qm by r minus d the whole square, and B2 will become equal to mu naught by 4 pi qm by r plus d the whole square. Net magnetic field will be how much? B axial will become equal to B1 minus B2. Don't you agree with me? Because bigger is B1, smaller is B2. So B1 minus B2. Solve this. It will become mu naught by 4 pi into qm common, then 1 by r minus d the whole square minus 1 by r plus d the whole square. After you solve this, because I know the answer from first chapter, it is coming. You remember what is the answer for the first chapter? Electric field is equal to K 2 PR by r square minus d square the whole square. If you remember, in the previous chapter, first chapter, we got the value of electric field for axial point as K 2 PR by r square minus d square the whole square. Same way, if I am going to solve it, what I am going to get? Mu naught by 4 pi into 2 mr by r square minus d square the whole square. This is the magnetic field due to a magnetic dipole at an axial point. In last 7 years, I have not seen this derivation being asked in the board examination. They never ask. Not in book itself. Yeah, they don't ask. But this you should be remembering, it is useful. Though derivation is not required, but this expression is very useful. So magnetic field due to magnetic dipole at an axial point is given by the formula mu naught by 4 pi 2 mr by r square minus d square the whole square. And obviously, if r is going to be much more than d, then what will be B axial? Mu naught by 4 pi into 2m by r cube. Once again, recalling of the first chapter. There it was E is equal to K into 2p by r cube. Here we have mu naught by 4 pi 2m by r cube. Any problem? If you have any problem, please ask me. If there is no problem, I will go to the next derivation. I will not derive that much, I will directly write the expression. If you want, you can derive it later at your home. Because see, it is very simple, same thing I am replacing. If you go and see first chapter derivation, same thing will be there. Here it will be E1, Q, everything will remain same. E2, Q, everything will remain same. And finally, you will get, this only you will get. So I don't think it is wise to spend time and derive once again the same thing. Even it is not there in NCERT book as you are saying. So directly we can write for what is the magnetic field due to magnetic dipole at an equatorial point. Shall I write that? Can I go to the next page, guys, if you allow me? You are writing something? If you are writing, I will wait for 2 minutes, no problem. Yeah, I will wait for a minute, make it fast. Hemant, Sarukesh, Anbarsi, Sai Rakshana, Devadarshan, Amruta, Ananya, Sarvanan, I, Leah Varshini, Ivan. You people will wait till the class gets over. Don't go at 8:30, 8:40, 8:45. Usually at 8:45 you are going and having a dinner, no? Today you don't go and you wait till the class gets over, okay?
Just going to wash my face, sir.
Okay, Ivan, you go do whatever you want to do, but you be there by the time class gets over, because I will ask you to stay back I'll give some instructions for my Friday's class. That's why I'm saying. Nothing else.
Okay. Yes, sir.
Yeah.
Okay.
Okay.
Yes, sir.
Shall I change the page, if you permit me? Believe me, this derivation is not required for the school exam and board exam. It's not there in syllabus. I just did to make you understand it, the same thing. But this final expression is much required. And final expression you can write just if you remember this also. See, I am replacing k by mu naught by 4 pi, p by m, everything remains same. So, now you tell me, what is the magnetic field due to magnetic dipole at an equatorial point? First of all, tell me the electric field value. K into P. K into P by r square plus d square power 3 by 2. Same thing will repeat here. So, since electric field was K into P by r square plus d square power 3 by 2, here if you have a dipole QM and QM, let me assume one south pole and one north pole. From center, if I go axial distance r away, one will be repelling, one will be attracting, net field will be here. Remember all these things? Same like the first chapter. And what will be the value of this B equatorial? This will become equal to mu naught by 4 pi into m by r square plus d square power 3 by 2. And if it is true, then for r much more than d, B equatorial will become equal to mu naught by 4 pi into m by r. Any problem? I hope there is no problem. If there is any problem at all, please ask me. Can I proceed? Can I proceed? Take more.
Yes, sir.
Okay. If you're writing, take 1 minute and finish writing fast. I hope you have copied. Once again, in the first chapter, after this topic, what came? Dipole placed inside uniform electric field. Same will happen here. Next topic is magnetic dipole kept inside. See, I am saying one thing to you once again. In NCERT book or in any school exam also, in board exam also, instead of writing magnetic dipole, they may write short bar magnet. Don't confuse yourself. If I say short magnet is kept in the magnetic field, or I say magnetic dipole kept in magnetic field, they both are same, because short magnet is only magnetic dipole. So, magnetic dipole kept in uniform magnetic field. So, suppose if I am keeping in magnetic field, what I am keeping? My magnet QM, maybe south pole, north pole. So, by the principle of torque, there will be, what is going to act? Torque will act, and torque will be how much? What was there in electrostatics? Q is equal to Pe sin theta. What will be here then? Torque equal to Mb sin theta. Understood? Can you recall that same thing came in the previous chapter also? NIBA sin theta. NIA is M, so MB sin theta. I am not justifying you that how M came. That is different topic. But the similar thing came there. So, torque is given by the formula MB sin theta, where M is the magnetic moment, B is the magnetic field. Torque is given by, or if I write in vector form, torque vector is equal to M vector cross B vector. So, if a question is asked, when will a short magnet experience the maximum torque, theta is 90 degree. Minimum torque, 0 or 180 degree, isn't it? Okay. If you have written, if you have understood, then next topic. This is a quite interesting and important topic. Give the heading as current carrying loop as a magnetic dipole. Current carrying loop as a magnetic dipole. So, if you are done with whatever I have taught till now, give the next heading as current carrying loop as a magnetic dipole. In bracket you can also write electrostatic analog. Electrostatic analog. NCERT writes like that only. In bracket you can write electrostatic analog. Electrostatic analog, analog, because NCERT writes the same word, that's why I am writing the same word as NCERT. Okay. Now please drop your pens, pay attention. Something new came which is not there in the previous chapter. So I am asking you to be concentrated. You should understand this. So heading says that current carrying loop as a magnetic dipole. It somehow means that if you have a loop carrying current, then this loop is behaving like a magnetic dipole. See, it is true. How I will prove now? But it is true because in the previous class I told you about paramagnetism and ferromagnetism. There I told you electron is moving in circular path. So it is becoming a magnetic dipole. And I said you all the dipoles which are in paramagnetic materials, free electrons are available. Those free electrons are having dipoles. Since they are randomly oriented, it does not produce any magnetic field. But if they are aligned to direction of magnetic field by giving external magnetic field, it behaves like a magnetic substance. Now we are going to learn and we are going to prove how this circular current carrying conductor is equivalent to a magnetic dipole. So now I want you to recall what we have learnt in the previous chapter, moving charge and magnetism. We have derived magnetic field due to circular current carrying conductor at an axial point. You remember this? Radius A, distance R, the magnetic field here is equal to mu naught I A square by 2 into A square plus R square power 3 by 2. Those who were there in the previous class, previous chapters class, I have derived it deeply. And those who were there in Sunday's class, I have even recalled this in Sunday's class. Moreover, in Sunday's class, I have recalled more than this, which I have not done in the regular class, and I have told you one expression. I am going to derive it now once again for the regular people also. But this is clear to you what I have done now? This expression is remembering? You are remembering this expression? This is the expression for magnetic field due to circular current carrying conductor at an axial point. At the central point, it is mu naught I by 2 R. If you go R distance away, it is mu naught I A square, where A is the radius, divide by 2 into A square plus R square power 3 by 2. If R is the axial distance, A is the radius. Okay. Now, in this expression, if I multiply and divide by pi, so I can write B is equal to mu naught I into A square into pi divided by 2 pi into A square plus R square power 3 by 2. Or one thing I will do, I'll why to make it more complicated, I will take a condition. Before this itself, I will take one condition, or let me take after this also, no problem. So I can write, if R is much more than A, that is the axial distance is much more than the radius. This I have talked in Sunday's class. what will happen? A will get neglected and I will get the value of B as mu naught I A square by 2 into R cube. Am I right? Because A square will become 0, R square power 3 by 2, 2 gets cancelled, R cube. I hope nobody has doubt in why I am not eliminating A in the numerator, because a very small number in multiplication will affect the answer, but a very small number in addition or subtraction will not affect the answer. 0.000005 plus 100 will not change the value much, minus also will not change the value much, but 0.00005 multiplied by 100 will change the value much. So, in multiplication and division we cannot neglect the small quantities, but in addition and subtraction we can neglect the small quantities. That is why in addition I neglected the value of A. So, I got this. Now, from here you write, it will be little easy. So, when I take, let me erase this step and yeah. Now, let me write after this step that multiplying and dividing by pi. So, B will become equal to mu naught I into pi A square by 2 pi into R cube. Okay. I will do one thing, I will multiply by 2 pi and divide by 2 pi. See, I want to bring something which I want. So, I am doing all this, already 2 was there. I will write here, you will not forget it, multiplying and dividing by what? 2 pi. Since I multiplied and divided by 2 pi, I got this expression. Now, what will happen, you see, B will become equal to mu naught into I into 2, what is pi A square? Its area, divided by 4 pi into R cube. Any problem in this? I will just write in more rearranged way, I will write 2IA, it will look more better, 2IA. So, I got, please pay attention, I got magnetic field due to circular current carrying conductor at an axial point if axial distance is much bigger than the radius of the circle as mu naught by 4 pi into 2IA by R cube. Clear? I hope it is clear. After this, in electrostatics, if I ask you what is the electric field due to electric dipole at axial point if axial distance is much more than the value of d. Very good. Electric field is equal to K into 2P by R cube. You remember this? You remember this? From beginning of today's class, I am insisting and telling you that there is an analogy between electrostatics and this chapter. Now, see here, K constant, R cube, 2, P, this IA must be some kind of magnetic moment. Do you understand this? I hope you are understanding this. Because there is an analogy between electrostatics and magnetism. If you see here also electric field, one more thing is there. One thing is this is coming. Second thing is, it means that circular current carrying conductor is also it is electric dipole. It must be a magnetic dipole. I hope you are understanding this. Since these two expressions are very analogous, I can conclude that circular current carrying conductor is also behaving like a magnetic dipole and its magnetic moment is I into A. For n turns, NIA. So, now we came to know that magnetic moment is equal to IA, and that is why it is ampere into meter square. This thing we used in the previous chapter. NIA is equal to M I took. Something I hope you understood. In the board exam, this question has come. How it has come, you know? Prove that circular current carrying conductor is magnetic dipole if its axial distance is much more than its radius. This question comes, if you understand this concept, you can easily you can prove it. Otherwise, you will confuse what they have asked. If it is clear to you, you can copy it. See how I have written is in this direction. My flow chart is like this. Don't confuse and write here and there. Whatever. My flow chart is like this. It will disappear, no? It will remain like this itself. I thought it will disappear. Sorry. Nothing like that. Size I cannot control here.
Sir, you can control, sir. There, above, no, sir.
Above it's there.
Sir, I want star and small.
You want to demanding. Okay. This is the order of how I have solved. Okay. Write in the same way. First you write this, then 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 you write this, and finally you write this. Don't confuse and write here and there. In exam, you will forget what I taught. If anybody has doubt, feel free to ask me. If there is any doubt, please feel free to ask me. We are almost towards the end of this chapter. I will give some questions now which came in the board examination. Some interesting questions are there. Which one?
There will be one circle.
This question. We'll explain. If you are done, let me know. And how you should conclude, you know, how you should conclude it. You should write like, therefore, a circular current carrying loop behaves as a magnetic dipole. Circular current carrying loop behaves like a magnetic dipole. That's why in the previous class I told you, if electron is revolving, it is going to become a magnetic dipole.
Sir, complete, sir.
Good, everybody is done? Yeah, still doing.
For this circular loop.
Circular loop?
Is
Yeah.
this one current carrying loop or is it magnetism, sir?
Current carrying loop or?
This is current carrying loop or magnetism, sir? Magnet.
Current carrying loop will behave like a magnetic dipole, so it will have magnetic field around it.
So it's current carrying loop.
Circular current carrying loop behaves equal to a bar magnet, small bar magnet. So if I have a circular current carrying loop, if I have a circular current carrying loop or I have a small bar magnet, they both are same. That's what I am trying to prove it now. That's why the topic name is electrostatic analog. That is the heading, right? And what heading I gave you? I gave the heading to you as circular current carrying loop as a magnetic dipole. That's what I meant. I meant that if you have a circular current carrying loop, it behaves like a small short magnet. This question has come in the board exam to prove this. That's what you have proved now. Okay. Now take one question, please. 2 minutes. I'll take out a question. Question is two small magnets are placed horizontally. Their north poles are at 30 centimeter east and 20 centimeter west. 30 centimeter east and 20 centimeter west from a compass needle. If the compass needle remains undeflected, compare the magnetic moments of the magnet. Tell me, Anshul. Somebody saying something?
You teach from compare.
Compare the magnetic moments of the magnet. Compare the magnetic moment of the magnet. I hope you have written. 9 by? No, not correct. Anybody else?
27 by 8.
27 by 8 looks little correct. Anybody else? Cube, no it is. Okay, how the question goes, I'll just explain it to you. Can you read the question, Shweta?
Two small magnets are placed horizontally. Their north poles are at 30 centimeter east.
One second. From, there is a compass placed between them, and from the needle, one is 30 centimeter? 30 centimeter east.
Yeah, east.
Oh, this one is 30 centimeter. Sorry, east means that side, no? 30 centimeter east, okay. And second one is 20 centimeter west, okay. What they are asking further?
If the compass needle remains undeflected,
Hmm.
where the magnetic moments of
So they are asking that needle does not deflect, it remains static. When it is possible? If both the magnetic fields are equal. So magnetic field by this pole and magnetic field by this pole should be equal. I have taught to you how to calculate magnetic field by a single pole. Mu naught by 4 pi qm by r cube. I told you. Or if you want to write in terms of axial point, the formula is B is equal to mu naught by 4 pi into 2m by r cube. Am I right? They may have different pole strength. Who told they have same pole strength? They cannot be? Who told they are dipole? Hey, we are using the formula for this separately and that separately I will use. It will have its own m1 and I will write b2. b2 will become equal to mu naught by 4 pi, it is a constant, into r1 cube. I am writing 2m2 by r2 cube. Can I write like this, Karthikeya Palan? M means qm into 2d. They may have different qm also. For same magnetic field, you are telling distance is different. Yes, qm also is different. Are you getting my point? So they may have same magnetic field value, but the magnetic moments may be different, will be different because distance is not same. If this compass would have been in center, then what you are saying is fine. But now it is somewhere else. It means qm is not separate. It is different. So now, what will be b1 by b2? Tell me. Mu naught by 4 pi. Everything will get cancelled here. Why I want to write? Everything gets cancelled. If I divide both, 2 gets cancelled. I am going to get m1 by r1 cube into r2 cube by m2. Am I right? Now, this value is given as what? b1 is equal to b2. That is, for no deflection, for needle to be undeflected, what should happen? b1 must be equal to b2. So if b1 is equal to b2, then I am going to get m1 is to m2 is equal to r1 by r2 the whole cube. Do you agree? m1 by m2, r1 goes there, r2 comes down. Now what is r1 value? What is r1 value? 30 into 10 to the power minus 2 divided by, since we are going to multiply, it is in division, we cannot take, let us not take out, no problem, cube. This 2 gets cancelled, it will become 3 by 2 the whole cube. So it will become 27 by 8. So m1 is to m2 will become 27 by 8. I hope you understood. This kind of questions can come. It's not very difficult question. But your brain should work that they are not deflecting, they should have same magnetic field. And you should use the correct formula. So are you seeing how the questions are going to come from here? Take another question to have more clarity. If you are copying, make it fast and take another question for better clarity. Shall I give? Shall I give? Question is two short magnets. Two short magnets. I told today, short magnet means magnetic dipole. Yes, two short magnets of magnetic moment A and B. Two short magnets of magnetic moments A and B in bracket you can write A is equal to 32 ampere meter square. They should directly give right there A and B. A is equal to 32 ampere meter square and B is equal to 27 ampere meter square. So, A value is given as 32, B value is given as 27 ampere meter square. Are placed as shown in figure. Are placed as shown in figure. Find the magnitude of the magnetic field produced by these magnets at a point P, at the point P. I hope it is clear. A and B means its magnetic moment is, how much is given A for? 27, 32, for B 27. I hope it is clear. This point is P. They are asking you to find the magnetic field at P. Basically, it is a question of equatorial point. Try to solve this. Be careful. Magnetic field is also a vector quantity like electric field. So, be little careful. Solve calmly, don't be in a hurry. Please tell me, Devadarshan.
2 micro Yes, sir.
2 micro Tesla.
Yes, sir. P.
Okay, let me check it. So Devadarshan is telling the answer as 2 micro Tesla. Let me check. Others, any answer?
Sir, you want in vector form or magnitude?
I want the magnitude. They told magnitude alone. I hope you are solving. I'll solve it at the end. Don't worry about that. But please solve by yourself. Give a try at least. This is the way the questions are coming from this topic. Shall I solve? At least I'll tell the way of solving. Let the answer be secondary. Minus? Minus what? Loudly here.
1.5 into 10 power minus 4.
Tesla. I don't know. I'll check. Okay. So please pay attention. Everybody now, pay attention. I hope everybody is understanding that this point P is equatorial point for this dipole also and for this dipole also. So let me consider this magnet first. I am taking it as magnet 1 and I am taking this as magnet 2. So for magnet 1, what will be the direction of dipole moment? South to north, right? So what will be the direction of magnetic field? 0. Direction opposite to it. You remember equatorial point. So direction of B1 will be like this. That you are understanding first. That are you understanding first? If you remember the derivation of minus Q plus Q, electric field like this, like this, like this. This is direction of dipole moment. This was minus P cap. You remember this first chapter? Same like here also. If the magnetic moment is from south to north, magnetic field will be from north to south. Same way here, if the magnetic moment is going to be from south to north, the magnetic field will be from north to south. We will find B1, we will find B2, then by vector addition, the net B will be root over of B1 square plus B2 square plus 2B1 B2 cos 90. It is going to be 0. So B1 square plus B2 square. Okay. I hope you understand this. This much you are understanding, the logic you are understanding. If somebody has problem in this logic itself, ask me and learn how it is coming. Because this logic is more important than the solution. After this it becomes child play. Formula based now. Because B1, the formula is mu naught by 4 pi into m by r cube, isn't it? So the formula of this value is known to you, this value is known to you, r is known to you, put in this equation. Same, what will be B2? Mu naught by 4 pi into, it will be m1 by r1 cube, it will be m2 by r2 cube. So if you want me to solve it further, this will become 10 to the power minus 7 times, what is magnetic moment for A? 32 divided by, what is R1? 40 into 10 to the power minus 2 the, I don't like all this. Okay, anyhow. What to do? I can leave, you cannot. 10 to the power minus 7 into, what is this? 27 divided by 30 into 10 to the power minus 2, power whole cube. Cube and all this should not give. Okay. Now this will become, I am solving.
27 and 3 cube cancels.
Yeah, that's why I am solving.
This one 1 by 2, sir.
This will
52 by 64.
10 to the power minus 7 into 32 divided by 40 into 40 into 40. Very good, easy only. And 0, 0, 0 will become 10 to the power 3 and it will become 10 to the power minus 6. So it will become 10 to the power minus 3. I hope you are understanding what I am doing. Okay. This becomes 2 times. So it will become 0.5 times 10 to the power minus 4. Anybody has problem in this? Tesla obviously, not denying that. Next here, once again 10 to the power minus 7, something like that will happen. Yeah, it will happen, definitely it will happen. 3, 3, 3. See, if I take a question from book, if I don't give my own values, they are making the question such that it will not trouble you much. 27 into 10 to the power minus 3, same thing will come. So you are going to get 1 into 10 to the power minus 4. Mr. Yogit, you added both 1 and 1, 0.5, 1.5 you wrote. Huh? This 2 you got and then you told the answer as 1.5 times 10 to the power.
Sir, if you do the vector addition, I got root 13, I took 3.2 into 0.5, I got 1.5 some approximation, so I did like.
That only you did, no? Thank God, then no problem. Then your answer may be right also. So B is equal to root of B1 is this 0.5 times 10 to the power minus 4 square plus, what is this? 1 into 10 power minus 4 square. If I am a student, what I am going to do? 10 power minus 4 square I will take common, isn't it? Then what remains? 0.5 square here plus 1 square, isn't it? Then I will not solve. After this you solve, something is going to come into 10 to the power minus 4 only is going to come, that I am very sure. Now root of 0.5 square is 0.25 and then 1, so 1.25 root over, definitely it's less than 1.5, how it can be? Root of 1.25 is definitely going to be less than 1.25, right? So it cannot be 1.5.
Sir, for me root 5 by 2 10 power minus 4.
So that is approximately, I can tell 1.12 approximately. Yeah, that makes little sense. So magnetic field value is approximately 1.1 into 10 to the power minus 4 Tesla. Yogit,
Sir, 40% correct.
they won't give marks for 40% correct. So you don't expect 40% marks. Actually, they should give marks if all steps are correct. There only they'll get half marks for you. If it is 3 mark question, 2.5. Yes, Mr. Pratap, ask me.
I got 1.18.
You got 1 point?
118.
That is very more accurate, good. I wrote 1.1, you wrote 1.118. What else you want? 3 decimal point correct. Good man, I appreciate. I hope it is clear to everybody. I hope it is clear to everybody. Any problem in this? Okay. One topic was remaining, now only I saw while seeing the question. Shall I go to that topic? One small topic. It will not take much time. Yeah, potential energy only. So shall I erase, shall I go to the next page? If you are copying, 1 minute you take and copy something. Don't start copying the answer fully, just the concept you copy, fast. Time is 8:50, people automatically started dropping by themselves. Sarukesh Thambi, don't go. Video off, then he will also off in some time. Shall I continue? Farzana, shall I go to the next page? Thank you. Okay, now heading, last heading is potential energy of an magnetic dipole kept in magnetic field. Potential energy of magnetic dipole kept in magnetic field. Yes, exactly. Not tau, U is equal to minus mb cos theta. That's same thing. So I will write directly by analogy, but I will draw the diagram. I will draw a magnetic field. In this magnetic field, I will keep a small short magnet. And please understand, very similar to, Yogit, please, 1 second. Very similar to what we did in second chapter. What we did when we kept a electric dipole, I said you, if you have uniform electric field and this uniform electric field, if I place a electric dipole and if I move from theta 1 angle to some, suppose I am moving like this, theta 2 angle, then what is the energy stored in that? U will become equal to m, not my, that is final expression, mb cos theta 1 minus cos theta 2. You remember, not mb actually, p. This was p in that chapter. Those who are not remembering this, I will repeat for them. I said that whenever you have a dipole kept in electric field, I am talking about second chapter now, electric field, it has a tendency to align with electric field, right? Torque will act on it and make it to get aligned to the electric field. If you hold it and you turn it in the opposite direction, then some energy is stored inside it and it will come with that energy back, isn't it? So, how much is the energy stored when you turn a dipole from theta 1 angle to theta 2 angle can be found by this formula. This we derived actually in the class by integration. Same way, by analogy, if you have a magnet at an angle theta 1 and you turn to a new angle theta 2, what will be the energy stored? M B cos theta 1 minus cos theta 2. Where, what is theta 1? Initial position or initial angle. What is theta 2? Final angle. That is from which angle to which angle you take. If we assume that theta 1 is 90 degree, because 90 degree will give maximum torque, sin 90 is 1. So, if theta 1 is 90 degree and theta 2 is theta, then what will happen to u? It will become minus mb cos theta. You remember this expression? It was minus p cos theta in the case of electrostatics. In magnetism, it is minus mb cos theta. This is the energy stored inside the magnet when a magnet is rotated inside the magnetic field. So, whenever a magnetic field is, magnetic dipole is given some torque inside the magnetic field, it will store energy of minus mb cos theta. After this step, same like the electrostatics, we have three scenarios. If theta is equal to 0, stable equilibrium. If theta is equal to 90, neutral equilibrium. If theta is equal to 180, unstable equilibrium. So, in theta 180 degree, what will happen to u? U will become minus mb. Example of stable equilibrium. When you have, yes, when you have 90 degree, u will become 0, which is neutral equilibrium. And when you have 180 degree, you will become minus mb, which is plus mb, which will become unstable equilibrium. From? Yeah, obviously work will do mb only. I hope it is clear. If it is clear, copy down fast. Copy down fast, and after copying, Pratap, you have asked me something. I will keep a separate session for you to clear that. Okay. I will send you a link, not now, tomorrow maybe, and I will clear the things for you. Okay. And SSM Nagar students can wait. They don't want to drop. I told you so. I will give some instructions for tomorrow's class, not tomorrow's, Friday's class. So you will stay back. Others can drop after copying, except SSM Nagar students. Others can drop after copying this topic.
Okay, sir.
Yeah.